So we were also looking at specific heat, the concept of specific heat of a gas. Suppose we have a particular gas. We have this particular gas which contains a lot of particles. The concept of specific heat is the following: when you provide heat to the gas, it results in some rise in temperature, and we know that the rise in temperature is proportional to the heat supplied, and this concept will be molar specific heat. This formula is quite similar. Delta Q is mc delta T, but instead of m we have small n here, where n is the number of moles. So molar specific heat is heat supplied per unit rise in temperature per mole. How much heat do you need to raise the temperature of 1 mole of a gas by 1 degree Kelvin or Celsius? So that is specific heat. Yes. So in a gas, first we will consider specific heat at a constant volume. So what we are doing is, suppose if I supply heat to the gas and the gas expands, so all the heat is not going to increase the internal energy, because when the piston expands, the gas is going to do work also, so some energy will get lost there. First we are considering the simplest concept, which is specific heat at constant volume, which means that all the heat that we are supplying to the gas is going to increase the internal energy of the gas, and we know the formula for internal energy. The internal energy of a gas is F, which is degrees of freedom. Each degree of freedom gets half kT of energy, half kT into n. N is the number of particles, so internal energy of a gas is F by 2 n kT, and if we transition from this constant K to constant R, it can be written as F by 2 n RT. This is the formula for internal energy of a gas. Now the next concept is, we will supply heat to a gas and calculate its increase in internal energy, because all the heat that we are supplying is gonna increase the internal energy, because constant volume, the gas cannot do work. This process is a constant volume process. There is no displacement of the piston. Work done by gas is zero. So we can say the change in internal energy is change in F by 2 nRT, which is F by 2 nR change in temperature delta T. Now if we compare it with the definition of molar specific heat, we arrive at the conclusion that Cv equal to Fr by 2 by comparing these two equations. Yes. So Cv is Fr by 2. Now let us write down the specific heat for these three gases. Monoatomic gas, F is 3. For monoatomic gas, monoatomic gases have 3 degrees of freedom. So 3R by 2. Diatomic gases have 5 degrees of freedom, Fr by 5R by 2. Triatomic gases have 6 degrees of freedom. So 6R by 2. So the formula for internal energy. Now let us rewrite the formula for internal energies of a gas. These formulas are extremely important. These are all the formulas for internal energy that we know. First formula, this. Internal energy is NCV delta T. This comes from the very definition of Cv. This is basically, this definition is the definition of Cv. On the left hand side, technically we should have heat supplied, but we know that when the process is a constant volume process, heat supplied is also the change in internal energy. So change in internal energy is NCV delta T. For different gases, we know that Cv equal to F by 2R. So we have this particular formula. Change in internal energies F by 2 nR delta T. This particular formula. And if we write down this same formula in terms of K, it is F by 2 nK delta T. So this is the formula for change in internal energy. The formula for internal energy written in terms of Cv. So it's the same formula that we started with. We started with this particular formula. This particular formula. This formula is the same as this formula. But often you will see the first formula appear more often than this particular formula. So you should be familiar with all of them.